So I want to show a couple of things in terms of you walking away, making sure you understand. And one of them is this hand-in homework that you owed me yesterday. So I just want to comment on it a little bit so that you have a sense of what's going on. I want to make sure you understand the big picture. That's what I'm after in terms of a test we got coming up in a little bit. So, and also because this is just such a cool problem. So just as an example, let's just pick one of these. I don't know, that one right there. So what's the probability that 75 people show up for this flight, given that you have booked, and this is cool, although there's, and this is not obvious, although there's 76 seats on this plane, the airline decided to book 80 because they knew that not everybody shows up. And again, it's interesting to calculate. I didn't ask you to do this, but to calculate the mean, since the mean for a binomial distribution is n times p. So in this case, n is 80, not 76. And I don't think that's obvious. If you multiply that out, you get 74.9, roughly 75. And so what does that mean? Well, that's the expected value. In other words, on average, you'd expect 75 people to show up for the flight. Well, perhaps that's exactly why the airline decided to book 80 people, because if 75 people show up for the flight, awesome, there's 76 chairs. And so that's kind of good. Like that's exactly what you'd kind of want to happen. So I booked 4 more people than fit, and each person is $400. Hey, I just made 1,600 extra bucks. Now, what's interesting though, if you go on to calculate, and this is the kind of thing I would want you to be able to do on a test, like be able to think, be able to reason. You have a formula for the standard deviation, which is the square root of n times p. Notice we already figured that out a second ago, but then also times q. So p is the probability that you're interested in, which is people show up for the flight. Q is the probability then that people don't show up for the flight. So this would be 0.064, and that's found by going 1 minus, since the sum of all the probabilities is always 1, it's basically the probability of success, people show up, times the probability of failure, they don't show up. And so if you multiply that out, you get 2.2. And so what I would hope you understand then is that it would be usual. It would be usual for the mean plus or minus 2 standard deviations. So if I take 74.9, and again, I didn't ask you this on here, but I want you to understand it. 74.9 plus 2 2.2s, you get approximately, let's see how to write this. You get 79.3 on the upper end. And so would it be unusual for 79 people to show up? The answer is no. And maybe that's not good, because remember, we only have 76 seats. But if I go to the lower end, the mean minus 2 standard deviations, I get 70.5. And notice again, this is and one of the reasons I'm showing you this, besides I want you to learn something and make sure you're taking in the reason that I had you do this. Notice those come out decimals, and that's not so good because, well, a binomial distribution is not decimals. Like you can't have 70.5 people show up. And so that's one of the reasons 7.1 is kind of cool, because we're talking about continuous data. Here, I can't be continuous. I have to round this off. I don't know whether to call this 70 people or 71 people. It's right in the middle. This one probably feels maybe more like 79. But basically, it would be usual for somewhere between 70.5 and 79.3 people to show up. And so as long as that number stayed less than 76, or I should say 676 or less, so I would be in trouble, according to this, if 79 people show up. I would be in trouble if 78 people showed up. I'd be in trouble if 77 people show up. So again, I'm not asking you this on this question or even on a test, But would you think that's maybe not a good choice? Maybe they shouldn't have booked 80 people. They should have only booked 79 or maybe 78. Does it make sense? This is the kind of thinking that would be involved in really using statistics for something. So that's just interesting. So this is not hard. You should be using your note sheet to do this. To get, for instance, all of these different answers, we said in our calculator that was binomial PDF. It asked for n, it asked for the percentage, and it asked for the number that you're particularly interested in here. And so that's where that 18% probability came from. So you have an 18% chance that 75 people would show up. And again, this is so powerful. I mean, I really hope you understand this. Notice lots of these probabilities are basically zeros. All of these are zero, but even some of these next ones are pretty much zero. You don't have that much of a chance that 61 people are going to show up. But notice the probabilities start to be sort of legitimate in here. There's a 2% chance, a 4% chance, a 7% chance, an 11% chance, a 15% chance. Notice though, interestingly, there's almost no chance that 80 people show up. So that's kind of cool. Like there's not a great chance that all 80 people would show up, which remember means you have 4 pissed off people that thought they had a seat, now they don't, right? But true to what we calculated here a second ago, notice there's a 3% chance that 79 people would show up, meaning you have 3 pissed off people. There's a 7% chance that 78 people show up. Now you got 2 pissed off people. There's a 13% chance that 77 show up, which means you've got 1 pissed off person. But remember, that's kind of cool for them because they collected 1,600 extra bucks and they can say, hey, anybody want to take another flight later, as I said? And so maybe this 1 pissed off person right here, because 77 people show up, you get them 400 bucks. And remember, we are trying to predict, we're trying to see what might happen. And this is the distribution of all the different things that could happen. There is a, 0.008, a point, I guess that would be 0.8% chance that only 69 people show up for the flight. And of course, you'd be happy then because you didn't have any problems. Nobody's mad. But look at these interesting questions that I asked. And I guess I'm just interested that you see this is easy because this is the kind of question I want to be able to ask you on a test. So making the probability distribution is the main thing. All those percentages there, I make them ultimately by cheating. There is a longer way that I showed you that you could also do, but on the test, you can choose whatever you want. Binom PDF. I see that I missed the F there. Binom PDF is the easiest way. And so if I have all these probabilities, now I can answer all kinds of interesting questions. Would you agree this is an interesting one? Find the probability that exactly 76 passengers show up. Well, that's easy because there's the percentage right there. Exactly 76. Notice that's surprisingly small. That's not a very big number. Other interesting questions. This is a very interesting one. What's the probability that the flight's going to be overbooked? In other words, too many people show up. Well, you should say that's not hard. What's too many people showing up? 77 is too many people showed up. So is 78, so is 79, so is 80. If I add all of those up, then I have my answer. Again, I think it'd be easier just to type all 4 of those in your calculator. That's not, there's some shortcuts. I wrote one of them right here, but let's not talk about that. It's just add those 4 together. Now, again, I think that's interesting because this basically says you have roughly a 24% chance that too many people show up for the flight. And what that really means is that, well, I guess 76% of the time, you're fine. Does that make sense? Remember, you're talking flight after flight after flight after day after day after day, airport after airport after airport. You're talking about billions of, well, maybe billions are too big, but 1 million flights over the course of a year. And 76, 3/4 of the time, you got no problem. 24%, you got a problem. But you have a way to handle that. Like I said, you just offer those people some money. And so maybe that works out really good. So notice that's an extremely interesting prediction. It's not a report of the past, it's a prediction of the future. You can expect that 24% of the time you're going to be in trouble. And again, notice it's interesting, of that 24%, isn't this like half of it right there? Half the time it's only one overbooked. And so you only have one person to kind of satisfy. The remaining percentages get smaller, 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 to the point where this one is almost like never going to happen. You're hardly ever going to have 4 people overbooked and, you know, all really pissed off. So maybe that's why the person decided that, you know, booking 80 was a good idea. What's the probability there will be at least one empty seat? One empty seat. At least one empty seat. Well, isn't this one empty seat? If it's a 76 flight, if you have 75 people show up, then you have one empty seat. This is 2 empty seats. This is 3 empty seats. This is 4. Oh, okay. So what we're really doing then is adding all of these together. So this is question 4. Again, this the easiest way. It's not terrible. Just start adding all those up. But remember, as kind of a cool shortcut, since the sum of all of these probabilities, every single one of them through here is 1, does it make sense, since you were basically trying to add all of these together, does it make sense as a shortcut? If you wanted to, you could take all of these, add them up, and subtract from 1. Does that make sense? That would be okay too, if you think that's a little bit faster, there's less stuff to type in. You got to think a little harder to do that. And I'm not talking about this, but we've been talking about binom PDF only because I'm trying to keep it simple. But you do have a button in your calculator, binomial CDF, which actually adds all the numbers cumulatively. It adds them for you, everything less than that. So notice this command right here, binom CDF cumulative as a shortcut. What this does is, well, notice I put in my usual n, my usual probability, but then 75. And so what's that going to do? It's going to add 75 and everything less than that. So it's not just 75, it's going to be 75 plus 74 plus 73 plus 72. Well, isn't that what I drew right here in red a second ago? Was exactly that. So you do have some questions. You had some questions in your assignment that were asking you to add lots of things. And so there are some kind of neat shortcut buttons. But I think in terms of walking away, being able to do something, and also keeping it simple and being able to do it on a test, really the backbone of this stuff is just write out the entire probability distribution. And then whatever questions that involve adding a bunch of stuff up, just add them up. Like, don't worry about the shortcut, just add them up. Like, there's not that many numbers there. I'm not going to give you one on the test that was like your lab where you have 416 seats on an airplane. It's like you can't do that without Excel, but you can do a smaller problem like this. So again, I highlight this because I hope you see that as a very practical takeaway, a predictive takeaway for what might happen in this situation. And, you know, this is the kind of question I want to be able to ask you on a test. That's why I'm giving it to you as a hand-in homework assignment, so that you have some practice with it and some thinking. But you can easily just push buttons here and have no idea what you're doing. Like, if you're not learning how to think, if you're not asking questions, if you're not making sense of this, if you're just pushing buttons and you're in a sea of confusion, that's not hard to be. You got to put some thought into this. And now in section 7, which we need to jump into now, in section 7, we're sort of pushing a different button, right? We're using the normal distribution now, not the binomial distribution, but the normal distribution. And so that can be a little confusing. So let's talk about that. So I want to say kind of one more thing about maybe 7.1, but begin thinking about 7.2 even right now. So We said yesterday that 7.1 was the standard, not just the normal distribution, but the standard normal distribution. And standard, we said, meant it was basically in Z form. In other words, where the graph was centered at 0, so the mean is equal to 0. And then 1 and 2 were standard deviations. In other words, this is Z equals 1, this is Z equals 2, this is Z equals -1, this is Z equals -2. And I could keep on going to -3 and +3 and so forth. And so standard normal is just where you know the Z-score. And so quickly from yesterday, we said, well, there was sort of two types of problems that we could handle. And I hope you already played with your homework assignment question and you asked this. So we could say an answer question like, well, you know, what percent of people are above a Z-score of, say, 1.72? Again, that's what's cool about a Z-score. If your Z-score is 1.72, you know that you're higher than other people because that's positive, but it's not over 2, so you know you're not unusually high. You're up there. But what percent of people are not at that Z-score, but above that Z-score? So again, drawing a picture over here, you would say, well, I guess 1.72, since this is 2, would be about right here. So I'm basically talking about, you know, what's that percentage right there? And we said yesterday that was the norm. I forgot, norm dist, was it? Norm CDF. Normal cumulative distribution function. Cumulative because, well, just like we talked about a minute ago, we're not looking for one particular probability. We're looking for a whole bunch of them. That's why it's cumulative. And so we said yesterday, the syntax of this is you've got to put the lower limit in. Based on this picture, I would say that lower limit is 1.72. But what's the upper limit? What's the Z-score out here to the right? How far does this graph go? It goes forever. So that upper limit is a Z-score, but there's actually no end to it. So put some gigantic number. And again, your book, I'm not purposely not even going to talk about this, but your book has you put in a number with E in it that is, you know, complicated, but it's like, don't make this complicated, just put some big number in there. Again, I'm always finding myself kind of being lazy and saying, well, I'll put 99. Like a Z-score of 99, that is way out there. Even 9 would have been fine, we said yesterday, but let's just put 99. So because this said above, that means its upper limit kind of wasn't given, like we got to supply that ourselves. And then because this is a standard normal distribution and we're talking about Z-scores where the mean is 0 and the standard deviation is 1, then that's what I'm entering. And so, and again, I should think, well, that's a pretty small percentage. Again, you should type this in with me. When I do this, I get 1.72, upper limit 99. So being able to say, oh, that's 0.0427. On the test, I'm not going to talk about rounding, but you know, roughly it's 4%. So there's only 4% of people that are up that high. Cool. Secondly, we said, what's the other thing I can do? Normal CDF took a range and it kind of spit out a percent. But inverse normal does the reverse. What if you know the percent, but you'd actually like to kind of spit out the range or the Z-score that would produce that? So the kind of question that was in your assignment or that I would put on a test would be something like this maybe. So if I say, okay, I'm interested in the middle. Let's do the most challenging questions here. Let's say I'm interested in the middle 60% of people. Notice I already know the percentage. So I'm not using norm CDF because that produced a percent that answered the question, what's the percent? And we ended up with a percent for an answer. Here I already know the percent, it's 60%. But what I'd like to know is like what defines that? What Z-scores define that middle 60%? Again, it's a good idea to draw a picture of this. So I draw a normal distribution. I know the middle is at 0 because this is a standard normal distribution. And so I say, okay, cool. Well, there's the middle 60% right there. And so what I would like to know is that Z-score and that Z-score. But we said yesterday, according to syntax, that inverse normal only operates where you can put in the area to the left only, unless you have an advanced calculator. The area to the left only. Does it make sense? 60% is not the area to the left. If you put 60% here, do you understand what your calculator thinks you mean by that? I'm going to erase this, but it means this. Since this is 0 and this is 50%, like this is what it would think you meant. Area to the left, 60%, that's area to the left forever. Is that where my 60% was? No, I had the middle, I had 60% in the middle. But you can recreate this. If you know that you have 60% there and the area under the normal curve is always 100%, then that means you have 40% left over, 20% of which would be here and 20% of which would be there. So actually, if I wanted that first Z-score, notice the area to the left of that. Whoa, that was a mistake. The area to the left of that is, well, 20%. So if I put 0.2 in here, and then I have to enter the mean and the standard deviation. So if I type that in, inverse normal, area is 0.2, I get negative 0.84. My first thought is always, you know, that like anything can come out of the calculator. I have no idea, 1957, but I just stop and think about it. And then I think, oh yeah, I guess that does make sense. It would be negative because I am over here on the left-hand side. And so that kind of makes sense. And so, yeah, I think that actually is probably right. So that's kind of this Z-score. So anybody, any Z-scores below that would be in the bottom 20%. Anybody above that would be in the top 80%. So we also said yesterday, it's kind of cool to note that because of symmetry here, don't you already know the right answer to this one up here? 0.84, not negative 0.84, but positive 0.84. If you wanted to check that, again, from here, what's the area to the left? It's not 60%, it's 60 and 20. So if you said inverse normal of 0.8, since 60 and 20 is 80%, and then 0 and 1, then you would indeed get that same answer. So you don't necessarily have to know that cool shortcut. So normal CDF and inverse normal, that's kind of the two basic questions. But now let's start. Now let's kind of make this a little, a little bit more useful and begin talking about 7.2. Which is just applications of the normal distribution. Not the standard normal, but just a normal distribution. In other words, the mean is no longer 0. As I said yesterday, that's kind of weird to have the mean be 0. Hardly ever is the mean 0 in the real world. And the standard deviation is no longer 1. Again, I consider this to be one of the the big takeaways from this class. So is the binomial distribution, because there's lots of places in life where there's only two choices, and the data itself is whole numbers. But secondly, there's all kinds of applications where in the real world, the data is normally distributed, and your ability to kind of predict the future is really powerful here. And so this is cool. Now, fortunately, it's no different. It's the same two commands. We're going to be using normal CDF still and inverse normal. It's just that, well, as I said, it's not going to be that the mean is 0 and the standard deviation is 1 anymore like it was in these problems. So it's kind of a little bit more realistic. So an example. Let's stick to something that hopefully feels good to you. We've been saying in this class that people's average temperature is around 98.6 or 98.7 degrees, somewhere in there. And standard deviation has maybe 1.2 degrees or something like that. And so what I would like to predict, keyword predict, is the percent of people who just kind of run hot. Like you were to take their temperature, for most people, it'd be like, oh, you have a little bit of a fever, your temperature is 100 degrees. But based on this mean and this standard deviation, are there people that just run at 100 degrees? I would guess so. So what we're talking about now, if we were to draw a graph of this, is no different than before. It's a normal distribution, except for at the center of this is 98.6 now, not 0. So this hasn't been cleansed. It hasn't been cleansed by turning it into a z-score. We don't have a z-score for anybody yet. Now, we won't do this, but as a side note, could you, I'm going to erase this, but could you find that z-score right there? Isn't that z-score that percent minus the mean? Isn't this the formula for the z-score divided by the standard deviation? Could we turn that into a z-score and then do the same thing we just did a minute ago? Yeah, but the cool thing is we don't really need to. We can just let the mean not be 0 and the standard deviation not be 0 and not bother to make this calculation. That's just kind of a cool shortcut. And so I'm interested in, and I don't really know where to draw this, but if this represents not a z-score, but actually just a temperature of 100 degrees, I'm just interested in what this percent is right there. What percent of people run that hot? Remember, I'm thinking of this as a doctor. If somebody comes in and they have a temperature of 100, do I freak out? Well, I probably would if this percent was really tiny, like 0.2%, and somebody came in and said, yeah, I'm always 100 degrees. You know, I think, well, that's a tiny percentage of people that are like that. But what if this percentage is actually pretty high, like 8% or something like that? Well, it's like, yeah, I'm not worried about you. That's really kind of normal. Again, what are we doing with, and notice I'm asking for a percentage here. So which one are we using? Are we using normal CDF or are we using inverse normal? I don't know how clear my note sheet is on this, but you want to kind of be able to read this. Yeah, it's normal. You want to kind of be able to read this for the test, because notice what does normal CDF do? It returns that probability or that percent. Again, I like the word probability because we're trying to predict the future here. So that's the one I want because I'm being asked for a percent. So not hard. I say, what is normal CDF cumulative distribution function? My lower limit is 100. This time though, what's my upper limit? Before it was always a z-score. So I was thinking, oh yeah, a z-score of 9 is really high. But now I got to think in terms of the situation I'm in. Like, what's a high temperature? What's my upper limit? This is my lower limit. I can clearly see that on the graph. But what's my upper limit? Just don't pick something too small. Don't say 105 degrees because people are 105 all the time. What should I put there? 200 degrees, 999 degrees. I don't know, just some huge number. Remember, this goes forever. Of course, that feels unrealistic. People cannot be 999 degrees. Certainly, you're going to be on fire if that's the case. Just put some big number in there that's realistic. Well, actually, maybe it isn't realistic. So I don't know. I could put probably like 150 degrees, and that would probably be plenty big enough. Does that make sense? Notice if you start at 100 and you go a standard deviation of 1.2 to make it to 150, that's a lot of standard deviations. So again, it's probably safer just to put 999 in there, but even 150 is going to give you a fine answer. But the difference here is you don't have to put in the mean is 0 and the standard deviation is 1. Just let it be what it is. The mean is 98.6, the standard deviation is 1.2, and that's going to produce the percentage of people out there. You should push these buttons with me just to make sure that you're tracking. Second distribution, lower limit 100, upper limit 150, mean 98.6, standard deviation 1.2. Mine produced a fairly large percentage. So that's rounded to 4 places. That's like, whoa, 12% of people. So again, that's as a doctor, that's a pretty high percentage. So if somebody came in with 100-degree temperature, I would say to myself, well, there's 12%. The normal distribution would predict 12% of people are going to be higher than 100%. So I'm not that surprised. That's a pretty big percentage. Just out of curiosity, if I went back in and put 999 in there for the upper temperature, I got, actually on my calculator, you might do this with me, but I got the exact same answer out to like 9 decimal places. It didn't make any difference. So again, I just want to make sure you're thinking in terms of common sense. We were given that back here. From where? That would be the first part of this class. That would be you taking the temperature of like 1,000 people and then asking what is the mean and the standard deviation of that. And you'd say, oh, okay, based on my study of 1,000 people, then that's what the standard deviation is from person to person. So you would discover that based on a study. And I haven't started talking about this yet, but that's the gist of kind of your final project. I would like you to find some data that you find interesting. And when I say find, it's ideal if you have some way to collect it, because it's just more fun if you can collect the data yourself somehow. It's a terrible way to do it, but maybe it's as simple as Facebook, like you just put out a post. The terrible part of that is you only get the people that respond to stuff like that. And then of course it's just your friends. So that's not a very good random cross section. But you could also just find it online, find the data someplace. But being able to get these two numbers yourself in the real world, armed with a bunch of data, that's kind of cool. And now we're making this prediction entirely based on that. Again, I would argue, do you agree that temperature seems like one of those things that would actually be normally distributed? You'd have tons of people here in the middle. If you collected data, you'd have tons of people here that hung around 98.6, a little high, a little low maybe. And you'd have less and less people that were way out here and less people that were way up here. And so that kind of seems like an example of something that would be normally distributed. So what about this? What about a second question on the same scenario, same picture, but would it be realistic for people to be under, say, 95 degrees? I think of that as being like hypothermic. So is that unrealistic? Are there people what's the percent of people that actually have a normal operating temperature that's actually under 95 degrees? Is that realistic? Is that way too small? Again, it sort of feels like it to me. Like I don't think of anybody as being that cold. You could look on your phone, but I think you're starting to, at 95, you're already kind of talking about hypothermia. But again, I'm asking for a percentage. So do you still see this as normal CDF? But remember, lower limit, upper limit. What's 95 here? Is that lower or upper? Upper. That's why it's important to draw this picture. The lower limit is over here. So 95 is actually the upper limit. What should you call the lower limit? Some small number. It could be 80 degrees. That'd probably be close enough. It could be negative 50. Just make sure it's some number that's really small. If you want to be sure, make it negative 999. Yeah, 0. That's plenty close enough. 40 degrees, I'm sure would be just fine. But anything, any number you want to stick down here, just don't say 94. That's not far enough to the left. But yeah, maybe 0. But the point is, you're not doing this based on logic. I mean, you're not doing this like, oh, it's impossible to be below 0 degrees. No, this goes forever. That graph goes until you're at negative 50,000 degrees. I mean, is that realistic for a human? No, but this graph goes forever. So you just have to think about the scenario. Well, you know, multiples of a standard deviation of 1.2. I mean, if I went 3 of those, remember 3 standard deviations is pretty far. 3 of those is only like 4 degrees. So if I even went down to 90, it's probably going to give me about the same answer as if I stick in 0. And the mean has not changed, and the standard deviation has not changed. Is that a tiny percentage of people? Let's find out. $95. Yeah, I got a really tiny number. Did you get this? 0.001. 95. This is not 0.95 degrees. It's 95 degrees. So that's just not a decimal. So what can be confusing about this is these aren't percentages. Does that make sense? These are 98.6 degrees, 100 degrees, 95 degrees. Those are whole numbers. Those are not decimals. And so, you know, my conclusion there is, wow, that is not very many people. I mean, I guess that's kind of why that's called hypothermic. Like people just aren't down there. Notice that's 0.1%. It's not 1%, it's 0.1%, like 0.1%. So if somebody's down there, that's weird. That's strange. That's not just, oh yeah, no problem, you're fine. No, there aren't very many people down there. There's almost like no people. This is really low, really small. This is something you really want to practice a bunch. I've put a lot of days on the schedule. We're going to sort of continue talking about this the rest of the week because I want you to get it so deeply. I want you to, because I hope you see how useful this is. Go ahead.
It was on the homework, it was the one where you were comparing the percentages. So like what the input rule
Right.
would be. And I noticed they were different. And in this case, so that's like the 95 is exactly 3 standard deviations out.
Oh, is it really?
The 1 point, yeah.
Yeah, you're right. It is.
I
didn't notice that.
So I thought, okay, well, it should be close to like whatever that percentage would be on the rule, but it's not. So I was just curious, like.
No.
I mean, it is close, but it's not like the same. So I was curious about the.
So everybody understand her point? If you go 98.6 minus 3 1.2s, you land exactly at 95. So that was actually 3 standard deviations below the mean, sort of accidentally on my part. And she was saying, hey, because it's exactly 3, then don't I know the answer to this based on the empirical rule? And let's see if I can pull, I don't think I saved the old note sheet. Let me see if I can pull it up really quickly though, because it is the same. Like it is exactly the same. Yeah,
Oh.
should be. I'll pull it up in my open math because that's kind of fast.
Well, if this says 0.0013, wouldn't it be point? Yeah.
Let's see, so what did we get a second ago?
But that's a little, like, isn't that a limited amount, though? That's just 0.15, but the other one would be. Unlimited.
So yeah, we were basically talking about this black percentage over here. Now, a second ago, what did we get? We got 0.0013, which would be 0.13%. This is saying 0.15%. I think it's just a matter of rounding.
Okay.
Actually, I think this one is the one that's rounded.
Okay. So
I'm not-
close, but-
Yeah, so I mean, it should be, in a sense, without rounding, it's exactly the same. I mean, they are off by tenths, hundreds, thousands, they're off by 2 10,000ths. So maybe it's just rounding, but but yeah, that's a really good observation.
I was just curious if you had a question about it.
And that's what's kind of cool about this, because you're no longer limited. You're no longer limited to just exactly 3 and 4 and 2. And so we can kind of go any place we want. Let's just look at one more quick example, going the other direction using inverse normal. So remember, inverse normal is where you know the percentage. And so what temperatures define the middle? Let's go 90%. So 90% of people, are in the center, right? And so that leaves 10% outside of that. And so again, maybe if you're in that middle 90%, again, the doctor isn't worried about you. So the question is, when should the doctor get worried about you? Well, if I think of this as the middle 90%, does it make sense? Okay, cool. That's the middle 90%. I am not worried. I am not worried about these people. I am worried about these people because they're too hot. I'm afraid they're going to have problems because they're too hot. I'm worried about these people because they're too cold. But of course, the interesting question is, how do I know who these are? Like, when is somebody in that category? Does it make sense that I need a temperature for these 2 locations? I need to know what those temperatures are. I'm worried about the people that are in these little tails out here. I'm worried about those people, but what's the defining line between those 2? And again, look at your note sheet just so that this is speaking to you. What does inverse normal do? It returns the limit defining that area. That's what I'd like to know, is what temperature defines those people. So since that's 90%, obviously that leaves 10% of people in those tails. And since this is the middle 90%, that means 5% would be up here and 5% would be down there. Notice I have to know that it's the middle 90%. If that's not exactly in the middle, then maybe it's not 5 and 5, maybe it's 2 and 8 or something like that. But it's the middle. And so does it make sense then for this temperature, that would be inverse normal? And we said area to the left. Well, what's the area to the left of that? 5%. And then we put in our mean and our standard deviation. In this case, we're leaving those alone. We're not doing this with z-scores. So it's kind of cool about this is we're not going to get a z-score, which isn't as useful. We're actually going to get a literal temperature. So inverse, you should do this with me. Inverse normal, 0.05, 98.6, and 1.2. I got 96.6. Notice that's actually a temperature. And so now I have my line. Anybody above 96.6, get out of here. I'm not worried about you. You're in the middle 90%. I'm not worried about you. If you're below 96.6 now, you're down there in this, well, kind of tiny percentage. Well, it's not tiny, but you're down there in the bottom 5% now. You're in the 5th percentile. And so now I am going to worry about you. And so now I have a temperature that defines that. One side, we're fine. Other side, we're not fine. Now, interestingly, what about this other temperature? Didn't we have like a shortcut? Well, that shortcut worked great when the middle of this was defined as 0, but now it's not defined as 0 anymore. So actually, I don't really have any automatic way to get the other answer. So you kind of have no choice but to say, okay, well, what's this location? Well, again, area to the left of that. What's the area to the left of this location? It's not 90, it's 90 plus 5. So it's actually 95%. And the mean is still 98.6 and the standard deviation still 1.2. What does inverse normal say about that? It says 100.6 approximately. Now, just as a side note, given that this center of this isn't 0, it's 98.6. Do you notice that if you went, in this case, you went 2 degrees below? You went exactly 2 degrees down to that side. Notice over here, you went actually exactly up 2 degrees. Like it is still in the center. It's just that those aren't the same number. One is positive, one is negative. Do you see this as a powerful predictive tool if you are somebody in the doctor world? Now, basically, as long as somebody falls between those two temperatures, I'm sort of not worried if someone is between 100.6 degrees and 96.6 degrees. I'm not worried about you. If you're outside of that, then I am worried about you. Super powerful predictive tool. Okay. All I want to do over the next couple of days is just deepen your understanding of this. Maybe, and certainly we'll have time either tomorrow. I'm gonna definitely be giving you time to ask me one-on-one types of questions about either the MyOpen math homework or maybe some of the labs we're working on or something like that. So that you're kind of making sense of this. But you can appreciate this is going to take some study on your part, because we talk about things one day at a time, and today we're talking about normal and inverse normal, but then we also just got done talking about binomial PDF. You can appreciate on a test, this could start swirling around in your head and you suddenly feel like, I don't know anything, right? On a daily basis, when I'm doing tonight's assignment, this is the only two functions I need, normal CDF and inverse normal. And it's like, that feels okay on that assignment. But can you appreciate, you got to put a different kind of study, you got to put a different kind of thought into this. You got to be able to kind of connect other things. There's two main scenarios we've been talking about here, binomial and normal, as in terms of two different distributions. How do I know, when to use each one? And again, that's why I'm giving you a test review that's online, so that you have a chance to kind of practice this all thrown at you at one time, so that you maybe have more of a chance of kind of not freaking out and making sense of it. But it's not as simple as just, hey, I got the assignment done. I hope you realize you've got to put some concentration into this to kind of make sense of it and be able to answer some, practical, interesting kinds of questions. Okay, I will shut up. And you're out of here, or as usual, if you want to stay after, you're more than welcome to